So, is this the one with charge A located 37 centimeters from charge B? I'll assume so unless you say otherwise. Yes, okay, cool. Let me just write it down before I put the screen back up. Charge A, 37, and you want to find where the electric fields are equal to 0. So let's say X is equal to 0 here. This is charge B with plus 22 microcoulombs. Charge A is 37 centimeters away. And it is plus 15 microcoulombs. And we want to know how far from A, all right, how far from A is the point where the electric fields add to 0. All right, so this is what I've got set up so far. Okay. All right, so we want to know where the electric fields are going to add up to 0. All right, so you might remember that the electric field due to a positive charge is going to point away from the charge, and the electric field from a negative charge is going to point towards the charge. Now we're talking electric fields here in both cases. All right, so we have two positive charges. So if we are over here, the electric field due to B is going to point towards B. So this is E due to B. And it's going to point towards A, which is in the same direction over here, E due to A. Over here, it's going to point towards A for A, and B is going to point towards B. In the middle, the electric field points towards A due to A, and the electric field due to B points towards B. Okay, so basically we want to find a place where they're going to add up to 0. Over here, they're always going to add up to a positive number heading to the right. Over here, they're always going to add up to a negative number heading to the left. So over here, E is always going to be positive. Over here, E is always going to be negative. But in the middle, E could be positive, negative, or 0, depending on exactly where you are. Somewhere in between A and B, we're going to find a point where the electric field adds to 0. So with this kind of problem, which we've seen on a couple different exams now with electric fields, electric forces, magnetic forces, you always want to set it up like this. Make yourself a coordinate system, plus X direction, and write down the directions of everything you're worried about. So we're looking for a place where the fields cancel, where the forces cancel, anything like that. Yes. No. Oh, shit. I do have my hours backwards. Sorry. If you see me doing things like that, tell me I'm backwards. Okay, so this is actually pointing in this direction. Let's see. Arrows point away from the positive charges. Okay, let's fix that. Away from the positive charges. Let's switch these around, A and B. So A points in that one, and B points in that one. Sorry. I drew it right here, and then I drew it wrong up there. Watch out for that. For me doing that. And this one was due to A. Okay, so, but the answer is still the same. It's going to be in the middle. So, basically, we want to find where E due to a point charge is equal to 0. We know E due to a point charge is K Q1, let's see, over R squared. If we put both Q's in there, then we're looking at the force and not the field. But I think this one asked us to find the field. Yes, where the electric field is equal to 0. Okay, so E at any point X, where X is somewhere between 0 and 37, is going to be K QA over RA squared plus K QB over RB squared. And remember, these Q's are going to be absolute value in here. It doesn't matter if I give you positive or negative here, you have to draw the picture to figure out which direction they're actually going to point. And RA is the distance from where we're measuring the field at X to A. RB is where we're measuring it to B. So RB is just going to be the distance between X equals 0 and X. So that's just equal to X. And RA is going to be the distance from X to 37, which is going to be 37 minus the RB distance, which is X. So this is going to be 0.37 meters minus X. This is the hardest part with any of these problems, and I think there might have been one on the last exam as well, is just setting it up so you've written both of these in terms of only one variable. So this is going to be equal to 0, and we're going to end up with K QA over RA, which is 0.37 minus X squared, plus K QB over X squared, value, is equal to 0. And then one of these, let's see, EA is pointing, sorry, EA over here is pointing in our negative direction. So this one picks up a negative sign. I move it over there, cancel out the K's. I'll end up with QA over 0.37 minus X squared is equal to QB over X squared. Okay, and now we just have to do some algebra. We know what QA and QB are, we're just solving for X. So if I cross multiply, QAX squared is equal to QB 0.37 minus X squared. So this is QA X squared is equal to 0.37 squared. Wait, I'll set that, leave the QB out until I factor this out. So let's see, we're going to end up with 0.37 meters squared minus 2 times 0.37 times x plus x squared times QB, QA, x squared equals QB, 0.37 squared minus, it's like 74 QB plus x squared QB. And then we'll take this and subtract it from that side. And then this is a 0. And then it's a quadratic formula from there. And once you've done the quadratic formula, you should end up with only two. Well, you'll definitely end up with two options. So let's see what these numbers actually end up being. This is QB over 7 squared. 74 QB plus x squared QB minus QA. All right, where's my calculator? Only one of your answers is going to make sense in terms of what you've set up here. So that's the one you're looking for. Okay, so we're going to end up with our x squared is going to be QB minus QA. We said QB was 22 minus QA, which is 15. I'm going to leave out the microcoulombs for now. So this is x squared times 7 minus 0.74 QB. So that's 0.74 times 22, 16.3, which is QB already, and that's going to be the X, because that's from this term down here, which should have been X next to it. And then 0.37 squared times 22. This is plus 3, just 3. Okay. So x equals the square root of plus or minus, no wait, it's minus b plus or minus the square root, b squared minus 4ac over 2a. So x is going to equal 16.3 plus or minus the square root of 49 minus 4 times 3 times 7, square rooted over 14. So let's see. So we're going to get 16 plus the square root of 49 minus 4 times 3 times 7. 16.3, sorry. 7 divided by 14. Nope, wait, that's not going to work. Did I miss something? Let's see. QB over here. This one was negative. That's positive. They do. All right, b squared. Oh, b squared. I squared a. Or I'm sorry, I squared a instead. 16.3 squared. This should be 266. All right, now I can do this. Okay. 266. Oh, okay. So one of our answers is 2.13 meters, or 0.201 meters. Okay, so this one is basically 20 centimeters. This one is 2.13 centimeters. Only one of them falls between 0 and 37 centimeters, so our answer should be 20 centimeters. Okay, and like I said, the hardest part of setting this one up is just drawing the picture and then setting this up with in terms of only one variable and not two, because you only have one equation here. You're halfway there if you set that up. You've got half the credit already. The rest is just doing the algebra. Let's look at the dot. Okay. Does anybody have any questions on that one? Or any others you guys would like to go over? I'm trying to put up the solutions to exam 3. I'll be able to do it after this. They're not working very well at the moment. Having PDF troubles. Laura's not here to save you tonight. She couldn't make it. She said she was going to watch it later, though, so hopefully somebody will pick up the slack and have some questions. Okay, well, while you guys are thinking about it, how about we take a look at the physical pendulum problem from the last exam, which I think is the one that most people screwed up at some point or other. Let's take a look at, let's say, we've got this version of it. There were 4 different versions. Oh, the same exam, part 2D, sure. Whoops, I lost it. Okay. Yes, and this was on a similar test. Okay, so let's see. An unknown element is mixed with the fluorine and sent into the mass spectrometer through the velocity selector. The element lands twice as far away from the center of the velocity selector as the fluorine. All right, so let's write this down. The fluorine had an atomic mass of 19. Mass of fluorine equals 19 atomic mass units. And it was missing 2 of its 9 electrons. So the charge of fluorine was +2. All right, and it says the unknown element, we want to find the mass of it. And we know it has 1 extra electron, so its charge of the unknown is -1. And it lands twice as far away as the first one. So the radius of fluorine is R. The radius of the unknown is 2R. Okay, so let's bring this back up. And we want to find the atomic mass of the unknown element. So this is what we know. Mass of fluorine is 19. The charge of it is +2. The radius is R. Mass of the unknown we don't know. The charge is -1. And the radius is 2R. All right, so we know that anything sent into a mass spectrometer is going to be subject to a constant B field. And its B field is equal to mv over qr, where r is the radius that it makes once it goes in, and q is the charge. So it comes through the velocity selector, goes into the field, and goes over here, or goes over here. And its radius r is this distance that it makes right there. And then this one over here would be 2r. Okay, so basically we're looking for the ratio of the masses of these two. Oh, it's complaining about my microphone. Hopefully you guys can still hear me. Let me know if you can't, or put it in the chat window or something. Okay, so let me solve this for the mass. The mass would be equal to B, absolute value of Q, R over the velocity. All right, so the mass of fluorine divided by the mass of the unknown is going to be the B field times the charge of fluorine, which was +2, times the radius of fluorine, which is R, divided by the velocity of the fluorine, V. And then for the unknown, it's subject to the same B field. It has a charge of -1, but its absolute value, so it's just a 1. It has a radius of 2r, and it had to come out at the same velocity because it went through the same velocity selector. So basically what we've done here is our b's cancel, our v's cancel, our r's cancel, and we're left with 2 over 2. So it looks like the mass of the unknown in this particular case should have been equal to just the mass of the fluorine, unless I read something wrong. This one was a little bit easier. Another way to put this would be to, well, I wouldn't do that because I didn't give one of these questions on any previous exam, but if I said it had to come through a something that accelerated it before it came out of the velocity selector, that could make it a little bit harder because they might not have the same velocities coming out. But we've only done the velocity selector problems, and basically this is just the idea behind how you solve it. Just make a ratio of these two things and cancel out everything that's the same. Let's see, are there any other questions on that particular one? Oops, this just keeps going from here. Let's see, there's a Gauss's law one on here. There's some circuit problems, some light bulb problems, resistivity problems, strings under tension. Ooh, this is a good exam. Yeah. Any others?
We do the Gauss's law.
Yeah, let's take a look at the Gauss's law one. Okay, let me go back to where I saw it. Okay, so Gauss's law, we've got a sphere inside a sphere. So there's one sphere here, and another one out here. This is radius A, and this is radius B. I'll bring the screen back up in a sec. The inner sphere is made of a solid insulating rubber. So this is insulator. And a total charge Q. And the outer sphere is a solid copper, which is a conductor, with a total charge Q. Radius B. And find the field at A over 2, E between A and B, X and B, and E is 2B. Okay, so let's bring this back up here. All right, so this is basically what we got. We have an insulator and we have a conductor. The thing to remember for Gauss's law, well, there's a couple things to remember. One of the things to remember for Gauss's law is that insulators can have a volume charge. And since there is a volume charge here, we're going to end up with the charge on the insulator is rho is equal to, let's see, it's going to be charge Q over the volume. So little q is equal to rho v. And then our charge Q on the conductor is instead only on the surface. So that's going to be a surface charge density sigma is equal to big Q over the volume A. This is going to be over volume B minus A. So conductors only have things on the surface, and that's the outside surface we're worried about. Insulators can have things spread throughout the volume. So the first thing we want to do is find the electric field at R is smaller than A. So we're going to draw our Gaussian sphere inside here somewhere at some radius R. That's supposed to be a circle. Okay, so Gauss's law, we've got EA is equal to Q enclosed over a constant epsilon naught. Oh, sorry, my mouse isn't right. All right, A is the area of our Gaussian surface. That one right there. Goes with the E field, which we're measuring on the Gaussian surface. This is the area of the Gaussian surface. This is a sphere, which has the area 4 pi r squared, where r is the little radius inside here, where r is smaller than A. So that's our A. Q enclosed is all the charge found within the sphere of A. If there were a conductor, there'd be nothing in there because all the charge is found on the surface, whether it's a hollow conductor or a solid one. But since it's an insulator, we have charge that can be spread throughout the volume because it's basically fixed where it is. It can't move around enough to actually move anything, if that makes sense. Sorry. All right, so our insulator here has some volume charge inside it, but we haven't hit any part of the conductor that has charge on it yet, so there's no other things besides the volume charge. So our enclosed charge is going to be a portion of little q. It's going to be our charge density, volume charge density, times the volume within R, which is going to be rho times 4 thirds pi little r cubed. All right, so our E field is equal to Q enclosed divided by A epsilon naught, which is going to be 4 thirds rho pi r cubed divided by 4 pi r squared. So the 4's will cancel out, the pi's will cancel out, r squared goes away. and we end up with rho r, oops, over epsilon naught. Oh, over 3 epsilon naught. Sorry, we still have a 3 hanging around that goes down to the bottom. So our E field at r is smaller than a is going to be equal to rho r over 3 epsilon naught. This is the only formula you need to remember to do Gauss's law. EA equals Q enclosed over epsilon naught. And you have to come up with a formula for A based on where you drew your sphere and what's inside the sphere for Q enclosed. So let's try part B, which is somewhere out here where we've now got an R that is between A and B. So E for R is greater than A but smaller than B. We're going to do the same thing again. EA equals Q enclosed over epsilon naught. A is equal to our Gaussian sphere, which is once again 4 pi r squared, but this is a different r this time. Q enclosed. Okay, Q enclosed goes all the way out to here this time. It includes all of the insulator, but the insulator doesn't go all the way to R. The insulator stops at A. So this is going to be rho times the volume out to A, which is rho times 4/3 pi A cubed. It does include some of the conductor, but it doesn't include the surface of the conductor. The surface of the conductor is still outside of our Gaussian surface. So it doesn't see the surface and it doesn't see the charge on it. It doesn't matter that part of the conductor is in here. There's no net charge on that part of the conductor. So we won't add anything to our Q enclosed there. So our E field is going to look a little bit different from last time because we've got R's in our A, but A's in our Q enclosed. So this is going to be Q enclosed over A epsilon naught. So E is going to be rho 4/3 pi A cubed over 4 pi A squared. 4's cancel, the R's cancel, but none of the A's and the R's do this time. So we get rho A cubed over 3, oh wait, I wrote R, that's an R, not an A. And then there's an epsilon naught in here somewhere, over 3 R squared epsilon naught equals A, where R is in between there somewhere. Okay, and then we want to look at it outside at any arbitrary distance, but I gave it at R is 2B here. All right, A is going to be out here somewhere. So now this is at some 2B. So this is going to be at 4 pi 2B squared, which is 4 pi times 4B squared, which is 16 pi B squared for A. Q enclosed. All right, now we've got two terms. The insulator is inside all of this, and so is our conductor. But they don't block each other. Doesn't matter where they are, insulator, conductor. If they're inside the sphere, you add them all up. So we're going to add our insulator, rho volume at A, plus we're going to add our conductor now that we've passed the outside surface. And we're looking at, we said for the conductor, it's going to be sigma. Oh, I put the volume down here. There should be an area. Sigma times the area at B, which is where the conductor is actually, where the charges on the conductor are actually sitting, is the outer surface of this. So Q enclosed is going to be 4/3 pi A cubed times rho plus, let's see, sigma times the area out here, which is 4 pi B squared. So E is Q enclosed over A epsilon naught. So this is going to be Q enclosed 4/3 pi A cubed rho plus 4 pi B squared sigma divided by A, which is 16 pi B squared. Something went wrong here. Aha, yes, A, I'm sorry. Yeah, oh, no, we're good. Yes, okay, because we're not at some arbitrary point, little r. In this case, little r is equal to 2b. I was like, why is there no r in here? It's because I didn't give you an r. R is 2b, that's why this all has b's in it here. All right, so the pi's will cancel out. Those show up everywhere. There's a factor of 4 that will cancel here, here, and here, leaving us with the last one. But that's the only thing that'll cancel. So we're going to end up with 1/3 A cubed rho plus B squared sigma divided by 4 b squared, and I always forget my epsilon naught. That should be down here too. Okay, whoops, bring that up just a bit. All right. Okay, the sphere problems are a little bit easier than the cylinder problems when it comes to Gauss's law, because the sphere has flux throughout the entire surface of the sphere. But there's one extra step you have to take if you're doing a cylinder problem instead. I don't want to go through a whole one, but I want to remind you of how that works. So let's say that we had a cylinder that encloses a infinite line of charge. So this is our line of charge, and it's got positive charges on it everywhere. And if we were going to draw something other than a circle to cover it, and that's a good idea here, a circle would be a bad choice. We want to draw our E field, which is always going to point straight away from our surface. E, E, and so on. E, E, E. And then we want to draw the area vectors for our Gaussian surface itself. A, 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 and all around. And then we've got a surface over here and a surface over here. But the thing to remember, you need to compare your area vectors A to your E vectors here. And the surfaces only contribute flux if E is parallel to A. Flux. Check mark. But if E is perpendicular to A, no flux. So when you do your EA equals Q enclosed over epsilon naught, this is all the A's with flux going through them. All surfaces with flux going through them. And none of the surfaces without it. So, in this case, we wouldn't count these outside surfaces here. The sphere only had one surface and it had flux going through it, so that was the one we used. But in the case of a cylinder, if you're putting something through the center of it like this, you only need the outside surface when you're talking about the area. Now, if instead you had, say, a sheet of charge with some positive charge on it, and you made yourself a cylinder that cut through the center of the circle, and then out the other side like that, so it was going through, let's see, solid lines through here, and I guess dotted lines through here to the other side. Now, when you draw your E field, it's parallel to the A field, or to your A vectors, on the edges only, but not on the top and the bottom. So here, we would have, let's see, the caps have flux, the side doesn't. Caps have flux, sides don't. In this case, the caps don't have flux. Flux, the side does. So if you end up with something other than a circle, draw the picture first and figure out which sides matter and which sides don't. I will guarantee you, if you have something with more than one side to it, something other than a circle, some of the sides don't count. So draw yourself a picture. If you're not sure you're understanding the question correctly, and that if you drew it correctly, come and ask me. I'm happy to answer questions like that. I'm not trying to trick you. Yeah. Any other questions you guys would like to go over?
For number 6 on the same exam,
Okay.
The equation to solve this is R equals the resistivity times length over area.
Yeah,
What
I don't think we used that on a previous exam, so we won't put it on. I won't put it on this one.
Okay.
Yeah, I don't think I put any resistivity questions on the resistor one. So anything from the resistor exam, if I gave you anything, it would be a simplification problem like this one. Like number 3 for that one. Oops. Okay. Do you guys want to go over one of the resistor problems? Or do you remember how to do that pretty well? Okay, well, unless somebody types something else and says something else, we'll do it a resistor problem for the benefit of people who might watch this later. Oh, let's see. Okay, we'll do simplification method, and let's do one of the ones where I put the battery in the middle, because that always seems to confuse people. All right, resistor here, and here, and here, and here, and here, and here, and then over here, let's put one here, and here, and here, and here, and here, and over here. All right, so we've got lots of resistors in here. There's a delta V over here. Let's call this R1, R2, R3, R4, R5, R6, R7, R8, R9, R10, and R11. Okay. I don't know if I'll actually assign values to these. I'll just go through how to do this quickly. Let's see if I have their color in here. All right, so the first thing I always recommend doing, this isn't not gonna, well, it's a slightly different color. Okay, let's see. One of the first things I recommend doing, or the first thing I recommend doing, is going through and drawing all of your currents. No matter which way you decide to solve this Kirchhoff's law's simplification method, put your currents in first. So the current starts from the positive terminal of the battery, which is this longer one. So it's going to come down here as I1, and then it's going to split. All right, let's call this one I2 that goes off in this direction, and I3 that goes off in this direction. I2 is going to get over here, and then it's going to split again. This is going to be I4 and I5. Then it's going to come back here to I2 and come back here to I1. I3 comes over here. It splits to let's see, we call this one 4, so this is going to be I6. This one's going to be I7. Then they come back together to I3, and then they come back together to I1 once again. All right, so for the simplification method, you want to find the easiest combinations that you're certain are either in parallel or in series. Don't start out with, say, over here where this one is in parallel with the combination of these two. Just start out with, hey, these two are in series. Let's start with those. R89 is going to be the sum of R8 plus R9, because that's how you add resistors in series. Let's see, R4 and R5 are in series, so R4, 5 will give us R4 plus R5. And R2 and R3 are in series. 2, 3 is R2 plus R3. All right, there's a couple other here that are in series, but it's not immediately obvious. So let's start with those, and then I'm going to draw myself the new version of the circuit with those combined. So that's positive, end of the battery. Come down through this one, and this one. Okay, I've got one here, and one here, and one here. And then this one. Whoops, nope, this is only one now. And there's one over here. So these are R11, R10, R8, 9, R7, R6, R4, 5, R2, 3, and R1. All right, so these two are now obviously in parallel. So R10, 8, 9 is going to be 1 over R8, 9 plus 1 over R10 to the negative 1 value. And these two are in parallel, so R2, 3, 4, 5 is going to be 1 over R2, 3 plus 1 over R4, 5 to the negative 1. So let's redraw it again. Oh, I forgot. What did I label that one? Oh, did I not even label that one? All right, this is R12. R12. All right, so we've got R12, R7, combined one now, and here, and R1, R2, 3, and R6. So R1, R2, 3, 4, 5, R6, R12, R11, R7, and R10, 8, 9. All right, now it's easier to see that these three are in series, and that these three are in series. So R on the right-hand side is going to be R1 plus R2, 3, 4, 5 plus R6. And R on the left-hand side is going to be R2, 11 plus R 10, 8, 9 plus R7. And then we're down to just a couple. We've got R12. And we've got R on the right-hand side. And now we've got R on the left-hand side. Okay, so let's see. What we've really got here is all the current goes through R12, and then it splits. So this is I1, and then the current splits. I3 goes off in this direction, and I2 went off in that direction. And then they recombine to get through the battery as R1 over here again. Since they all go through R1, but then, or 12, sorry, and then they split to go through these two are in parallel with each other, but they are not in parallel with R1, because the current that goes through R12 here then splits. Part of it goes here, part of it goes here. Only the ones that get part of it are in series with each other, not the one that went all through. So this is going to give us R left right is going to be 1 over R right plus 1 over R left to the negative 1. And now we've got R12, and one of our resistors, doesn't matter which side you put it on, left, right. And now these two are in series. So our equivalent resistor for this, is going to be R12 plus R left, right. And our very last circuit is going to look like this, with delta V and R equivalent. All right. So what would you do about the resistances at this point? Let's see. I've got a pencil, kind of. All right. So at this point, you can have R equivalent. Delta V equals IR. So I is equal to delta V over R. This is delta V at the battery. This is going to be R equivalent, and this is going to be I1, the one that goes through the battery. So this is how you calculate R1. And it goes around like that. All right, then we back up a step. We'll come over here and say, all right, I1 goes through the battery, goes all the way through here. We're good. All right. So the voltage of resistor 12 would be equal to resistance 12 times I1, the current that goes through it. The voltage of the left-right combination would be the resistance of the left-right combination times I1, which is also going through it. And the two of them together should give you the total voltage. So if you add this one plus this one, you should get back your total delta V of the battery. All right, so now we know the voltage, and we know the resistance, and we know the current through all of these. We back up another step to this one. All right, so we've got I1 coming down through here, and then I2 going this way, and I3 going that way. But these two are in parallel. So we know the voltage of one of these, left, right, is equal to the voltage at the left is equal to the voltage on the right. So if we know the voltage here, right, and the voltage here on the left, and we know the resistances, then we can get the current. Current on the left, which is I2, is going to be equal to VL over RL, and I3 on the right is going to be equal to VR over RR. And you've got all those values already, because you found them over here. Then we back up another step. The voltage on R7 down here is going to be equal to R7 times I2, because I2 goes all the way around here. The voltage on 10, 8, and 9 combination is the resistance of the 10, 8, and 9 combination times I2. The voltage on 11 is R11 times I2. And then the same thing over here to find the voltages on each of these. And then you know their voltages and their currents and their resistances, and then you can back up another step. At this point, the voltage you found for 10, 8, 9 is also the voltage on 10, is also the voltage on 8, 9, because those two are in parallel. Delta V, 10, 8, 9. So now you know the voltages at each of these drops, and you can find I5, which goes through this one, and I4, which goes through this one, and then do the same type of thing over here. And then you back up once again and say, all right, well, these are in series. When they're in series, they have the same current. So I4 is the same for this one, is the same for this one. I know the resistances. Delta V9 equals R9 I4. Delta 8 equals R8I4, and so on. And basically by doing that over and over again, you can back your way out to the entire thing. But I highly suggest drawing all these pictures because otherwise it's easy to get screwed up. So start with the basic circuit, simplify as much as is obvious, redraw it, do it again until you're down to 1. Then start backing up and finding the currents and the voltages across every single resistor as you go. And applying the 2 rules the whole way. In series, they have the same current, and in parallel, the branches have the same voltages. Voltage on each branch. Now, that does not mean that everything on that branch has that voltage. It just means the entire branch adds up to that voltage. When you do it for capacitors, so this is resistors, if you have a capacitor set instead, it works basically the same way. Parallel branches have the same voltage. Same voltage. And series resistors have the same charge. Charge Q. Okay. Any questions about that? Or anything else? Okay, well, if nobody else jumps in, oh, yes. Oh, what can you have for an equation sheet? Okay. Yeah, so I will once again give you the moments of inertia equation sheet. I will give you the Biot-Savart laws for magnetic fields, and I will give you the brute force equations for the electric fields, but you need to be able to do Gauss's law. All the other equations should fit on one sheet of paper, front and back. So you can bring an entire sheet of paper front and back, or you could bring all your individual equation sheets. That works too, whichever you feel like doing. Keep in mind that multiple different sheets had different things. Like I think K came up at least twice with 2 different meanings, and I came up at least 3 or maybe 4 times with different meanings. So don't just blindly copy your equation sheets on there. You might want to remind yourself what various symbols stand for as well. Don't put entire solved problems on the equation sheets, but you can write yourself notes like this I means moment of inertia, this K means the electric field constant. And I will give you constants and any conversion factors you need. Yeah. Well, unless somebody comes up with another one, I would like to show you guys how to do another physical pendulum problem, because that one is the one that most people did something wrong on at some point on the last exam. So let's take a look at another one. I did one on the previous review, so I don't want to do the same one again. I don't know what the last one looked like, though. Let's say that we've got... let's put a solid ball here and a hollow sphere there, and another solid ball over here. And we're going to suspend it from this point right there. Okay, so this is physical pendulum. All right, and let's say the rods are all massless in this case. This is going to have a mass of 5 kilograms. This one, or actually, let's just call this M1, leave it all in symbols, M2 and M3. Let's see. And I'm going to put y equals 0 down here, and this is the y direction up here. The rotation point is going to be at y equals 3 meters. This guy is at y equals 1.6 meters. This guy is at y equals 1.8 meters. So let's pretend this guy's a little bit higher than that guy. And this one has its center at y equals 0 meters. Oh, I'm sorry. Let's see. Oh, hey, yeah. Okay, I'm sorry if it's been doing that for a while. Did you guys get to see the actual one I did over here? I hope so. I put a lot of work into that. All right, I'll leave this up for a second, just in case that was missing from the recording. You can pause it if you want right there. Okay. Uh-oh. All right. Physical pendulum. Yeah. Let's see. Okay, so I drew myself a physical pendulum made up of 4 different masses. These 3, let's call this one a point particle. Let's say this is a solid sphere with a radius of 0.05 meters, or radius 1. And this is a solid sphere with a radius of 0.10 meters. And this is a hollow sphere with a radius, this is radius 3, this is radius 2 of 0.17 meters. Okay, so there are 2 parts to this problem when it comes to finding our, let's see, our period. So if we wanted to set this in motion and find the period, it would be 2 pi I over m g d. I is going to be the total moment of inertia of the system. Inertia of the system. Let's see, m is the total mass. G is just gravity, and d is the distance from the rotation axis. Oh, sorry, this wasn't a. All right, let's call it a mass at the rotation axis. Rotation axis. A mass at the rotation axis. So the distance from the rotation axis to the center of mass of the system. Center of mass of system. Okay, so how do we find the center of the mass of the system? That's a good place to start. Center of mass equations. It's going to be the sum of the mass of each object times its own center of mass divided by the mass of everything. So this is going to be mass 1, which was this one over here, times its center of the mass, which is at the center, and we set it y 1.6. y1 equals 1.6 meters. Plus mass 2, and I put mass 2 at 0 meters, times 0. Plus mass 3, its center of mass is at 1.8 meters. Plus mass 4, whose center of mass is at 3 meters. Divided by mass 1 plus mass 2 plus mass 3 plus mass 4. All right, and that will give you an actual number for your center of mass. Your D value is going to be your rotation point, which is 3 meters, minus your center of mass, which will end up around here-ish, cm, over here, minus y center of mass. And that's where you're going to get your D value from. All right, so now we need to find our moment of inertia. So we've got a point particle, we have 2 solid spheres and a hollow sphere. I for a solid sphere, which would be on your table, is 2/5 mr squared, and I for a hollow sphere is 2/3 mr squared, and I for a point particle is just mr squared. Yes, sure. Okay, so let's just set this up to find I. There's going to be an I value for each of these points, and for a point particle, the R in here is distance from particle to rotation axis. Particle to rotation axis. Yep. But the other R's are radii. Yes. And radius. So a point particle is automatically set up to go around the rotation axis, but anything else needs to use the parallel axis theorem instead. So we're going to get our total moment of inertia is going to be I for our solid spheres. So we've got one over here, 2/5 m1 r1 squared, plus m1 and d1 squared, where d1 is the distance from m1 to our rotation axis. So this is going to be d1. Plus our second solid sphere, which is 2/5 m2, sorry, m3, r3 squared, plus m3 d3 squared, where d3 is the distance from there to the rotation axis, d3. Plus m2, which is our hollow sphere, this is 2/3, m2 r2 squared, plus parallel axis for that one, m2, let's see, d2, which would be all the way up there, which is 3 meters. d2, which is equal to 3 meters. 3 meters squared. And then this point particle, which is actually at its center of mass, which means m4 times 0 meters squared. So basically, this is just equal to 0. So you'd plug these in, add them all up, and then stick everything up into here. And that's basically the idea behind the physical pendulum. Identify all of your masses, write down their moments of inertia, add the parallel axis theorem for anything that is not a point particle, and then find your center of mass of the system to plug in this d value, and you're good. All right, so number 7 from the previous final. Let's take a look again. Number 7. Okay. So you've got a long length of string. Oh, okay. 3.2 meters. Okay, so we've got a length of string that goes over a pulley. And there's a 5.5 kilogram mass hanging over here. We've got tension. The string has a mass of 186 grams. And we want to find the velocity of waves on the string. Oh, sorry, the length is 2.3 meters. We want to draw the fourth harmonic, F4. And we want to write the standing wave equation, y equals x of t, in the fourth harmonic. So we want to find omega and k and a. And at time 3.8, the amplitude of a point at x equals 0.25 meters. Okay, so let me put the screen back up. Center. All right, so this is our string. It's got a fixed end over here, and this is going to be a fixed end over here. And we're going to put a fourth harmonic in it. So I need 3 nodes. So it's going to look something like this. Only a little bit more even. All right, so we know that our velocity in the string, let me put some extra paper under here. A velocity in the string, of waves in the string, not the transverse velocity of the string itself, but the waves on the string, is equal to the tension, which we were calling F because T stands for period, divided by mu, which is the mass per unit length. Mass over length, so the velocity is equal to tension over mass times length, like that. So, velocity of waves on the string. Oh, we need to know the tension. Okay, so we said this 5.5 kilogram mass is stationary. So if we draw a free body diagram for it, we've got gravity going down and the tension force pulling up. And if it's stationary, that means the sum of the masses in the y direction, T minus Fg, is equal to 0. So tension is equal to mass times gravity, mg. But these are two different masses. This is the mass of the block, and this is the mass of the string. So the velocity is going to be equal to the tension force, which is mass of the block times gravity times the length of the string, divided by the mass of the string, square rooted. So this is going to be 5.5 kilograms times 9.81 meters per second squared times 3.2 meters divided by 0.186 kilograms. Let's see. So we're going to get square root of 5.5 times 9.81 times 3.2 divided by 0.186, 30.5. 30.5 meters per second is the velocity of waves on the string. And this is the fourth harmonic, so that's the next part. We also know the velocity is also equal to omega over k, but that's not necessarily going to help us. But we also know it's equal to the frequency times the wavelength. If we're in the fourth harmonic, L is equal to 2 times the wavelength right here, because we've got one wavelength here and another wavelength over here. So the wavelength is going to be L over 2 in the fourth harmonic. So that's going to be 3 over 2 meters, which is 1.6 meters. All right, so it means our frequency is going to be our velocity divided by our wavelength. So our frequency is going to be 30.5 meters per second divided by 1.6 meters. Let's see. 19.1 hertz. Okay, so this is our frequency at f4 because we're using our velocity and our lambda 4. Velocity stays the same, the frequency and the wavelength change. Okay, so we've got our frequency f4. Omega is equal to 2 pi times the frequency, which is going to be 2 pi times 19.1 hertz. Okay, times 2 times pi, about 120. Oh, sorry, is that what I said? 112. Sorry, no, 120. 120 radians per second, which means our k value from this equation up here, V times k is equal to omega, so k is equal to omega over V, which is going to be 120 radians per second divided by 30.5 meters per second. 120 divided by 30.5 gives us 3.93 radians per meter. So if we wanted to write our standing wave equation, we would say that y as a function of x and t is equal to 2a sine of kx sine of omega t, because that is our standing wave equation, x and t. Okay, oh, I must have missed something about the amplitude. Did I say something about the amplitude? Filling in the correct values, let's see. A long string. No, okay, I have not given the amplitude yet. I probably wrote something down to go with this. Velocity weighs on the string, because it turns out you can put whatever amplitude you want in there, so I must have actually just given them a number and realized that later. So it's going to be, let's say the amplitude. Okay, so it's the amplitude of one of the waves on the string which go down and constructively interfere in the middle, so you end up with twice the amplitude of that. So let's say it's 0.2 meters, which is ridiculous, it's huge, but whatever. Okay, so our amplitude will be 2 times our amplitude of 1, which is the amplitude of both together, is 0.2 meters, times the sine of k times x, so this is going to be 3.93 radians per meter x, times the sine of omega t, so omega was 120 radians per second t. All right, and that's our wave equation. So the last thing we'd need to put in here, we wanted to find the position of a particle on the wave, or is it a position or a velocity? We can do all of them. But anyway, the position of a particle on the wave at 3.8 seconds and 0.25 meters. Basically, that's what this whole thing is for. You just plug in those numbers in here. So that's going to be at x is equal to 0.25, t is equal to 3.8 seconds. So we're going to get 0.20 meters times the sine of 3.93 times x, which is 0.25, times the sine of 120 times t, which is 3.8. All right, and we should be in radians for this. So, mode. I think this is the only time you need to be in radians is for these wave equations. Times the sine of 3.93 times 0.25 times the sine of 120 times 3.8. Syntax. What am I missing? Oh, what is that? 0. All right. And our y position is negative 0.0752 meters. All right, so what this means is that if I started this going and took a picture of it at 3.8 seconds after I started, let's see, this is 3.2 meters long, so 2.5 meters would be like here-ish, 0.25 meters. I wanted to find my x or my y position of this location 2.5 meters from the edge at time 3.8. So it goes back and forth between these two positions. At 3.8 seconds, it is negative 7.5 centimeters below the equilibrium position.
I'm wondering how you found the amplitude that you plugged in.
Oh, I just
because you said you could put in any number, right? Or...
Yeah. Apparently, I didn't give one on the exam, so I'm sure the first moment somebody pointed that out, I made one up. So yeah, so I made that up. Okay. Yeah. Sorry.
No, it's okay.
If you see things like that missing, yeah. Usually, I've been trying to be better about that, but every once in a while, one of them escapes me. So yeah. Yep. But otherwise, I think we did we do something like this on the test? I don't know. We might have done something like it. I do like these kind of problems. There was definitely one on the homework like this. Yeah, but anything with the waves, I think we did a similar one, but we did it with a mass on a string instead. But it was a similar way of going about solving it, just using the energy that time instead, though. But there's still some standing wave stuff on there. Okay. Anything else you guys would like to see?
Could you do an example of one of the mirror problems, concave or convex, either one?
Okay, let's see. So for these mirror problems, we're going to have an optical axis. And let's start with a concave problem. Let's see. So if I drew the entire mirror, it would look like that, but this is probably the only part I'll be interested in over here. And if I drew the entire thing out, the center of curvature would be here, which means our focal point is going to be over here. And let's say I put an object in it right there. Okay, so let's say that our center of curvature is at 2 meters, which means our focal point is at 1 meter. Well, actually, let's make this 20 centimeters and just leave everything in centimeters like most stuff is. And 10 centimeters for our focal length. And our object distance, P, is going to be 15 centimeters. So it's halfway between the focal point and the center of curvature. So a common question to ask on this would be something like, draw the ray diagram and calculate the position of the image and the magnification, and make sure they actually agree with your ray diagram. So let's see, I don't appear to have a ruler, so I'll just make this up. All right, so to draw the ray diagram, let's see, ray number 1, and these would be on the optics sheet that I gave you guys, and I'll give you the same one on the exam. Let's see, and of course I don't have it with me, but I think ray 1 started from the top of this, goes over to here, and then goes through the focal point like that, and then the virtual ray goes off in the opposite direction. Ray 2 would go through the center of curvature and keep going. So of course, this is one of those things where you'd kind of have to extend it. It kind of comes from the center of curvature, comes in this way, and then comes back on itself. Sorry, kind of like that. Not this one. And then the virtual ray would go off in that direction, because the mirror would kind of extend out as a circle here. And then the last one goes through the focal point, hits the mirror, and then comes out parallel. So the virtual ray would go that way, and this one would go kind of this way. And obviously, I didn't do a great job of drawing this, because they'll come together somewhere down here. So basically, we're going to end up with an image down here somewhere. So my ray diagram predicts that I'm going to have a positive Q value for my image, because it's going to be on the front side of the mirror. It predicts that I'm going to have a negative magnification, which is greater than the height of the image object height. So it's going to be greater than 1, basically. And it's negative because I found them coming together below the optical axis. So I would draw it from the tip right here where they come together up to the optical axis from there. All right, so let's see if my calculations agree with that. We know that 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And if we want to find Q, this is going to be 1 over F minus 1 over P to the negative 1. So Q is going to be equal to 1 over the focal length minus 1 over the object distance, to the negative 1. Let's see. 1 over 10 minus 1 over 15 to the minus 1, 30. So I'm going to get 30 centimeters for Q. All right. I definitely drew it out at larger than 20, so far we seem to be agreeing. A disagreement would be something way over here, or something less than 20. Then you know you're wrong. But over here, that looks pretty good with my crappy drawing. So I'm good so far. M is equal to minus Q over P. So this would give me a minus 30 centimeters divided by P, which was 15 centimeters, which would give us a negative 2. This also agrees with my ray diagram. I predicted a negative magnification larger than the original. So the numbers I picked here just managed to come out to a negative 2. And basically, that's all we went over when it came to these. So basically drawing the basic ray diagrams and finding the image height and the magnification. The only way to switch things up would be to, say, give you the magnification and then ask you to find, say, the object distance or something like that. You'd need to know, or if I gave you the object distance and the magnification, you could use that to find Q and then work everything else backwards. So it's basically just these two major equations, this one here, and M is equal to minus Q over P. Any question I give you will be some combination of those. Let's see. Let's take a look at a convex lens instead. Or sorry, not a lens, but a mirror. So that would be one that kept going kind of over here. So that would be something, and then this would be the shiny side over on here. And that would have a center of curvature about here and a focal length about here. So this time, if our center of curvature is minus 20 centimeters, our focal length is negative 10 centimeters. And I'll put my object all the way over here, P at, what is that, maybe 40 centimeters? All right, so the first one you would draw comes in parallel, the first ray you would draw comes in parallel to the optical axis. And then it's supposed to look like it's going to go pass through the focal point. The virtual ray passes through the focal point because the focal point's on the opposite side of the image. And the actual ray goes up 180 degrees away from that. The next one would come in as if it were going to go through the focal point. So I'll kind of attach these two to this one. So it looks like it's going to come down and hit the focal point. But it's going to stop when it hits the mirror. And then it's going to come out parallel. So this one's going to come out of here going off in this direction, and this one, the virtual ray, comes off in this direction. The last one comes in as if it's going to hit the center of curvature instead. So I'm lining up the curvature point in the top of the mirror here. But when it hits, actually it just keeps going in that way for the virtual ray. Keeps going off through the center of curvature, and then the other one comes back on itself and goes off in that direction. So these three are coming together right before the focal point, and they're coming together above the optical plane to form a little tiny arrow. So this is predicts, this is going to be a negative Q. It's behind the mirror, so I should come up with a minus Q value just from everything that I put in there. It's predicting M is less than, the absolute value of M is less than 1, as it's going to be smaller than the original, smaller. And it's upright, so M itself is greater than 1, upright. Greater than 0, I'm sorry. All right, so let's try our calculation. Q is going to be 1 over F minus 1 over P to the negative 1. So this is going to be 1 over a negative 10. Whoops, not that one. Minus 1 over 40, negative 1. 1 over negative 10 minus 1 over 40 minus 1, negative 8. So minus 8 centimeters for Q, and the magnification is going to be minus Q over P, which is going to be a negative 8 over 40 centimeters, which is what, 1/5? So it's 0.20, positive. All right, so this is our Q and this is our M. And does it agree with our prediction? Yes, it does. We were going to get a negative Q, and we predicted it would be closer to the mirror than the focal length, which was negative 10, and we got negative 8, so that worked out perfectly. And we said our magnification was going to be positive, as in greater than 0, and it is, upright, and much smaller than the original. It is 1/5 of the original. So once again, my drawing agrees with my calculation, and they should. If they don't agree like that, if you end up calculating a positive or a negative or a positive Q, meaning you're forming something over here, or you've put it in here between F and C, but you've calculated it as less than F, you've probably drawn something wrong. And I will give you guys rulers on this exam, so you can be more accurate about this than I can be. Okay. And let's take a quick look at a lens problem, because that's another one that's kind of similar to these. And we only looked at converging lenses. We didn't look at diverging lenses. Okay, so let's say we've got a converging lens, and the converging lens has two focal points, F, and they both are positive. If we did diverging lenses, they'd be negative, but we didn't do that. So let's call these both 5 centimeters. And I'm going to put my object over here at 8 centimeters. P equals 8 centimeters. All right, and this is the center of my lens here, and all the refraction we pretend happens at the center. So my first ray is going to come in like this, and it passes through the lens and through the first focal point and off like that. I'll keep continuing this down, just in case. My second one goes through the second focal point, goes down till it hits, and we just continue the lens down. Imagine the lens is infinitely long if it goes below it, and then comes out parallel. And then the third one is going to go through the center and just keep going like that. Yep. My virtual rays would pass back this way, and this way, and this way. This time the virtual rays aren't converging, it's the real ones that converge. So if you looked into the lens from this direction, you would see an image forming over there. But you can also put a screen there and see your image forming, because this is a real image. The actual light rays are converging at this point. Should have mentioned, this one here, this is a virtual image. You can tell because Q has a negative value, and also because it's on the back side of the mirror. That wouldn't actually exist. Where's the other one I did? Oh, it's over here. All right, this one, this is also a real image. The actual light rays are converging at that point. We've got positive Q, actual light. So you only get a virtual image if you've got your virtual rays converging at that point, which you'll only get from a, oh, well, it depends on the configuration, I suppose, so I won't say that. All right, you can potentially get a virtual image out of that. I think you get one if you put the object within the focal length. But that's calculation to make, not something to memorize. All right, so our prediction is that Q is going to be positive, because remember, for a lens, the real light passes through the lens, so anything on the other side will give you a positive Q, a real image. A negative Q value would mean it's over here on the front side, being made out of virtual rays. I think it looks like M is going to be greater than 1. Our magnification is getting bigger. Sorry, M is, no, wait. Oh, but it's upside down. Never mind. Okay, so our magnification is going to be less than 0, but the absolute value of our magnification is going to be greater than 0. What am I trying to say here? My actual magnification is going to be negative because it's inverted, but it's going to be greater than 1 because it's larger than the original. So it's going to be a number larger than 1 in the negative direction. That's probably a better way to say that. And our Q value should be probably greater than P, but definitely greater than F. Because we put it all the way over here, and it looks like P might have been somewhere in the middle here. So we're probably looking for something 10 or larger for Q. So Q is going to be 1 over F minus 1 over P, the negative 1. This is going to give us 1 over 5 minus 1 over 8, the negative 1. Okay, 1 over 5 minus 1 over 8 to be minus 1. 13.3. Sounds good so far. So it's definitely larger than F, and it's even larger than P. So this would have been P, I don't know, maybe over here somewhere would have been 8, and now we're at 13.3. And M is going to be minus Q over P, which will give us minus 13.3 centimeters divided by 8 centimeters. About 1.7, negative 1.7 M, which again is correct. It's negative, so it's inverted, and it's larger than our original. Cool. These are basically all the mirror or lens problems. Now I could approach you from a different angle and give you M and ask you to find something else, but that's basically the idea behind all of them. Yeah. Anything else you guys want to see?
Will there be a dispersion? Well, could there be a dispersion problem?
Yes.
Like the prisms.
Like the prisms?
Yes, absolutely. So let's take a look. So let's say that you have light coming into some surface and then going out through a different surface. So let's say the light is coming in like this, and this is going to be air, and this is going to be water. So I've got basically a pyramid of water. So I've got my light coming in like this at some angle theta 1, and it's going to go from an n equals 1 to an n equals 1.33 system. So it's going to bend closer to the normal, like this. So I'm bending it closer to the normal and then just continuing it in a straight line. So this is going to be theta 2. And then when it comes out, it's going to come out at the new angle to the normal. This is going to be theta 3, and then it's going to go off again at some theta 4. And I could do this for, say, red light that might have an n of 1.33 in water, and for blue light, which might have an n of 1.60 in water, which is very large, but whatever. The first refraction will change a bit due to the index, and then the second one will also change. So you'll end up with one arrow that looks like this and maybe one that looks like this, and you're looking for the angle between them. All right, so let's go over basically how to do this. We'll start with one color of light. Let's say with red, which is our 1.33 equals N2, because we're going into the water. So we're going to do N1 sine theta 1 is equal to N2 sine theta 2. N1 is 1, and we're looking for theta 2. So theta 2 is going to be, you're going to divide N2 over here, and then you take the inverse sine. So this is going to be the inverse sine of N1 sine theta 1 over N2, where N1 is 1 and N2 is 1.33. And theta 1 is whatever angle going in that I gave you guys. So that'll give you your theta 2 inside. And then what you need to do is find this angle over here. Now to do that, let's say this is a right angle and this is a 30-degree angle, which means this one over here is a 60-degree angle. So if this theta 2 is whatever angle I get out of here, this is going to be 90 minus theta 2 over here. And this angle right here is going to be 180 degrees minus 30 degrees from here, and then minus 90 minus theta 2 from there. That's how you find this angle. And then theta 3 is going to be 90 minus all of this. Basically, it's just a matter of doing some geometry. Draw yourself a big one, a big version of this to work with, that kind of thing. So once you've got theta 3, or theta 3, which would be 90 minus all of that, then we would say that N2, which is the water, sine of theta 3, which is the angle on the way out of the water, equals N1, air, times the sine of theta 4, which is the angle into the air from this place, which is what we want to measure. So theta 4 would be the inverse sine of N2 sine theta 3 over N1. And then you've got N4, or theta 4 coming out. And then you just do this again for blue. But you change your N value to, say, 1.6. Same idea. And then you're going to take theta 4 for red and subtract it from theta 4 for blue, and you've got your angle of dispersion. Just take the positive value of it, whatever one is larger. Yep. The only thing to remember is the angle as you come in here is not going to be the same one going out unless these two surfaces are parallel to each other. And the whole idea behind dispersion is they're probably not going to be parallel to each other. The more times you make it hit a different type of surface, the more dispersion you're going to get. So you want to put a lot of angles in there if you want a lot of dispersion. Which is basically why we cut the surface of a diamond so many times and not just say, make it spherical. Yeah. Any other questions? Okay. Well, if you guys don't have any other questions, let's see. Some people are taking the exam tomorrow at 12:30. Some people are taking it Monday, Tuesday, or Wednesday. I will be on campus tomorrow probably from 8 until 10, but I have a meeting at 10. And then I'll be in the classroom from 12 to 12:30 before the exam if you come up with any other questions. Or you can try to find me after the exam if you want to ask questions for next week or make an appointment on Monday or something. Or Tuesday. I'll be around then. Oh, actually, no, I won't. I won't be around much on Tuesday, except for the exam in the evening. Okay? All right. Thanks, guys.